Today in this video, we'll be learning about the relationship between K, Q and G, the variables that we have learned in our previous classes. Also, we'll be looking at the factors that affect our equilibria.
Relationship between K, Q and G. Let us discuss the relationship between equilibrium constant K, reaction quotient Q and Gibbs energy change delta G. If the change in Gibbs energy is negative, then the reaction is spontaneous and proceeds in the forward direction. Whereas, if the change in Gibbs energy is positive, then the reaction is considered non-spontaneous. In such cases, reverse reaction would have Gibbs energy change as negative. Thus, reverse reaction becomes spontaneous. The reaction achieves equilibrium if the change in Gibbs energy is zero. At this point, there is no longer any free energy left to drive the reaction. A mathematical expression of the thermodynamic view of equilibrium is described by the given equation delta G is equal to delta G theta plus RT log Q, where delta G theta is standard Gibbs energy. Label it as equation 1. At equilibrium, when delta G is 0 and equilibrium constant is equal to the reaction quotient, the equation 1 becomes log K is equal to minus delta G theta over RT. Taking anti-log on both sides, we obtain the expression K is equal to exponential minus delta G theta over RT. Using the given expression, the reaction spontaneity can be interpreted in terms of the value of standard Gibbs energy change. If the standard Gibbs energy change is less than 0, then the exponential term becomes greater than 0, making equilibrium constant greater than 1. This implies the occurrence of a spontaneous reaction which proceeds in the forward direction to such an extent that the products are present predominantly. If the standard Gibbs energy change is greater than 0, then the exponential term becomes lesser than 0, making equilibrium constant less than 1. This implies the occurrence of a non-spontaneous reaction which proceeds in the forward direction to such a small degree that only a very minute quantity of product is formed. Factors affecting equilibria. Le Chatelier's principle. It states that a change in any of the factors that determine the equilibrium conditions of a system will cause the system to change in such a manner so as to reduce or to counteract the effect of the change. The effect of change of concentration, temperature, pressure, catalyst and inert gases on the equilibrium of a reaction has been briefed in the given table. Look at them carefully and notice the changes.
In this video, we'll be learning about the ionic equilibrium that is maintained in solutions. We'll be also seeing the concept of acid and base at brief.
Ionic equilibrium in solution. The substances which conduct electricity in their aqueous solutions are called electrolytes. Electrolytes, when dissolved in water, split up into charged particles called ions. The process is called ionization or dissociation. The type of equilibrium involving ions in aqueous solution is called ionic equilibrium. Certain electrolytes such as sodium chloride and potassium chloride are almost completely ionized in solutions. Such electrolytes are called strong electrolytes. Electrolytes such as ammonium hydroxide and acetic acid are weakly ionized. These are called weak electrolytes. In case of solutions of weak electrolytes, the ions produced by dissociation of electrolyte are in equilibrium with the undissociated molecules of the electrolyte. Acids, bases and salts are the examples of electrolytes and may act as either strong or weak electrolytes. Concept of acids and bases. Arrhenius concept of acids and bases. According to Arrhenius theory, acids are substances that dissociate in water to give hydrogen ions, and bases are substances that produce hydroxyl ions. A bare proton, H+, is very reactive and cannot exist freely in aqueous solutions. Thus it bonds to the oxygen atom of a solvent water molecule to give hydronium ion. This concept, however, suffers from the limitation of being applicable only to aqueous solutions, and also it does not account for the basicity of substances like ammonia, which do not possess a hydroxyl group. According to Bronsted-Lowry theory, acid is a substance that is capable of donating a hydrogen ion, and bases are substances capable of accepting a hydrogen ion. In the given reaction, the water molecule acts as a proton donor and the ammonia molecule acts as a proton acceptor, and are thus called Lowry-Bronsted acid and base respectively. The acid-base pair that differs only by one proton is called a conjugate acid-base pair. Therefore, hydroxide ion is called the conjugate base of acid water, and ammonium ion is called the conjugate acid of the base ammonia. Lewis acids and bases. A Lewis acid is a species which accepts electron pair, and a Lewis base is a species which donates an electron pair. For example, in the given reaction, BF3 does not have a proton but still acts as an acid and reacts with NH3 by accepting its lone pair of electrons. Lewis acids, electron deficient. AlCl3, CO3+, Mg2+, etc. can act as Lewis acids, while species like H2ONH3, OH-, etc., which can donate a pair of electrons, can act as Lewis bases.
In earlier videos, we have seen the concept of acid and base. In this video, we will be learning about ionization of acid and bases, with which we will also take a look at ionization of water.
Ionization of acids and bases. Acids like hydrochloric acid, sulfuric acid and nitric acid are called strong acids because these acids dissociate completely when dissolved in water and produces larger number of hydrogen ions. On the other side, acids such as acetic acid, hydrofluoric acid and carbonic acid dissociate only to a smaller extent in the aqueous solution, giving small amount of hydrogen ions, and hence are called weak acids. Likewise, few bases dissociate almost completely in the aqueous solution, producing a large number of hydroxide ions. Such bases are called strong bases. For example, sodium hydroxide and potassium hydroxide are strong bases. Bases like ammonium hydroxide and calcium hydroxide dissociate only to a small extent in aqueous solution and thus are called weak bases. Ionization of water. In pure state, water weakly ionizes to give hydronium ions and hydroxide ions. Applying the law of equilibrium, we get the expression for the dissociation constant. Since the concentration of water is very high and only a small fraction of it undergoes ionization, thus the concentration of water may be taken as constant and is combined with equilibrium constant K to have another constant Kw. Kw is called the ionic product of water. Its value is 1.008 times 10 raised to the power minus 14 moles square per liter square. The concentrations of hydronium ions and hydroxide ions are equal in pure water. Thus, in pure water, the concentration of hydronium ions and hydroxide ions is equal to 1 times 10 raised to the power minus 7 mole per liter at 298 Kelvin. The value of ionic product increases with the increase in temperature. The relative concentrations of hydronium ions and hydroxide ions vary in different solutions as shown.